So we will be discussing sampling rate conversion of band pass filter. So let me first write down the heading for that. Sampling rate conversion of band pass signals. Okay. So we know that any band pass signal can be converted into an equivalent low pass signal. Okay, whose sampling rate can be changed by already developed techniques which we have already discussed. Okay, we have already seen that the sampling rate conversion for a low pass signal. However, there are simple approaches are also there for concern band pass discrete time signal with integer band positioning, which we are going to discuss. So let me first write down. Let me just write down the same thing. Any band pass signal can be converted into an equivalent low pass signal whose sampling rate can be changed using already developed techniques. Okay, we have already seen different techniques for sampling rate conversion for a low pass signal. So what we can do, we can just translate or we can just convert a band pass signal to equivalent low pass signal, then we can use the same techniques. Okay. However, there are simpler methods exist. A simpler approach concerns band pass discrete time signal with integer band positioning. I will just explain that when I will discuss the integer band positioning. So if we want to be very specific for this, okay, so let me just write down. To be specific, let we wish to decimate by a factor say d. Okay. So an integer positioned bandpass signal with spectrum confined to the band, I'm just right, let me write that band. That's k pi by d, and this is k minus 1 pi by d. Okay. So the bandwidth for this spectrum is, you can say, it's just a pi by d. Okay. And k is some integer value. So that's why we are calling it integer position bandpass signal. Okay. And let me just write down k is a positive integer. Okay. So suppose we want to decimate by a factor of d an integer position band, that is given with this spectrum band. Okay, so let me just move to the next slide. There's no space. So a band pass filter, let me just write it down. A band pass filter. Okay, you have one for mod of omega from k pi by d to this is the other end, k pi by d. Okay, and zero otherwise. So that's a band pass filter. So we'll be using this to eliminate signal frequencies other than this range actually. Okay? So we'll be using this to eliminate the signal frequency other than this range. Then after elimination, then we will be doing a direct decimation of the filtered signal by the factor D that results in a periodic replication of the bandpass spectrum. Let me first sketch that part. Suppose you have a bandpass filter where you have input Xn and the output of this bandpass filter will be Vn. Then a downsampler. So that is giving us a Ym, which is nothing V of Md. So basically, after passing through a band pass filter, so which will eliminate the signal other than the desired frequency range. So then uh, uh, the output, this Vn, then Vn is passed through a downsampler. So this downsampler causes the periodic repetition of the band pass spectrum, which you know already, that causes the periodic replication of the band pass spectrum. What is that is V omega. So V basically is the V omega is the spectrum of this signal, which is the input to the downsampler. So uh, this downsampler causes the periodic repetition of the band pass spectrum V omega for every 2 pi by d radians. Okay, so it means you already know basically what a downsampler does. It causes the amplitude scaling, say by a factor of d. It causes the shifting of the spectrum. It causes the shifting of the spectrum, and the shifting will be of different values of say 2 pi by d uh, k. Let's take it L. So the shift where L is 0, 1 till d minus 1. Okay, so that will causes the shifting, basically shifting by say 0 causes spectrum shifting by that the second replica obtained by shifted at 2 pi by d. Third replica will be obtained at 2 into 2 pi by d. Then fourth replica will be obtained at 3 into 2 pi by d, and so on. Okay, so uh, then all these replicas will be added actually. So we'll see this with an example. Let's move to the next slide. So I was talking about the effect of the downsampling. I told you that amplitude will be scaled, spectrum amplitude will be scaled by 1 by d. That's the thing, first thing. I also told you there will be a replication and basically shifting of the spectrum, and those spectrum will get added. So basically shifted and added And the last thing which will happen is basically you have to do a frequency access expansion. Basically frequency access expansion. Basically this is nothing, this is a scaling of the frequency access. So you can say the spectrum of the decimated signal Ym is obtained by scaling the frequency axis by basically by d factor. Okay. So uh, there are three key points in the downsampling: scaling of the amplitude, creation of the basically replicas will be created, and all those will be added by those replicas are obtained by shifting, and then the frequency axis expansion. Okay. So now let me tell you an example for the case when k is equal to 3. So I told you that for a band pass filter, I'm taking the range say k pi by d from k minus 1 pi by d to k pi by d, and let's take k is equal to 3. When the k is 3, so this mod of omega will be uh, 3, and let's take d is equal to 4 also, 3 pi by 4, and this side will be getting 2 pi by 4. Okay, so for this range we'll be discussing uh, an example. Let's sketch that signal. Okay, suppose this is the spectrum of V omega, that's the output of a band pass filter, and let's say that is something like this, and this is say 2 pi by 4, and this is 3 pi by 4. Let's call this is a point pi by 4. This is your minus pi by 4, and this is your minus 2 pi by 4. This is your minus 3 pi by 4. Okay, so whatever I'm just doing, I'm doing for d is equal to 4 and k is equal to 3. Okay, so when k is equal to 3, you can say odd band position. Basically this is odd band position. Okay, so that's now one more thing you should keep in mind. Actually, okay, let me just put my, the spectrum, or this is the thing, this is a DTFT, and DTFT is not confined from minus pi to pi. Basically this, even this is having a periodic repetition within the band of 2 pi. Basically, okay, the same replica, the same thing is repeated in the in the in the in the band of say minus 3 pi to minus pi, and the same might be repeated in the band of say pi to 3 pi, and so on. So it will be repeating continuously. So it means these bands, basically this and these, all are available on the left side basically somewhere. Now uh, let me just sketch the y omega part. Let me keep this omega x only, and this is your y omega. And now the first thing is this part basically will remain same. This is 2 pi by 4, this is 3 pi by 4. Okay, and this will remain same. So this was minus 2 pi by 4, then minus 3 pi by 4. Now as I told you that the second replica you will be getting by shifting the same spectrum right by how much? By 2 pi by 4. Okay, so we can obtain that by shifting the spectrum by 2 pi by 4. So when you do that, basically when you do that, uh, what you will be getting, you are already having a spectrum somewhere on the left side. I think there's less space. Let me sketch it again on the next slide so the things will be more clear to you. Let me move to the next slide. Let let's look at this slide. Basically, you can see this is the TTFT of the output of a band pass filter. So this region, basically this region is nothing as a region of 2 pi, from minus pi to pi. Okay, so the same block will be repeating from the one which is repeating from minus pi to pi. The same spectrum will be repeating, let's say, from minus 3 pi to minus pi, as well as same will be repeating from pi to 3 pi. Okay, and so on. So that's the spectrum. Now let's here, basically here I have sketched the spectrum which is shifted by 2 pi by d or 2 pi by 4. So that's equal to pi by 2 basically. Okay, so uh, if one thing you can note that each of these is of pi by 4. Okay, each of these markers are for every pi by 4 interval. Now uh, if you want to shift this to the right by 2 pi by 4, it means this point will be something pi plus pi by 4. Okay, so you from here to here you will be getting this replica, you will be getting this replica, then this will be shifted over here and this will be shifted over here. However, let me just tell you one important thing. We will be concerning only in one band, other band need not to concern, means we'll be concerning only from minus pi to pi, so this is need not to concentrate more in. However, we will be concentrating on these replicas basically. Okay, because they are coming in from minus pi to pi band. Okay, now similar, now we will be shifting it again for 2 into 2 pi by d, that is 2 into 2 pi by 4, that's equal to pi. Okay, that's equal to pi, or that is also equal to 4 pi by 4. Okay, so 4 blocks will be shifted. So if I will shift this by 4, so first jump, second jump, third jump, okay, and the fourth jump. So it means this point will jump to this point. So that's the thing you can see here. We have just shifted it. Okay, so now this replica is shifted here. This will be shifted somewhere, which will go out of. Which will be shifted uh, somewhere out of the band of interest, other move far away from the pi, and this will be shifted to this location. Okay, so this will be shifted to this location. This is minus pi by 4. This point is minus pi by 4. Okay, so that's the second shift. Okay, since d is equal to 4, so the shifting, so we'll be getting shift up to the first shift was 1 into 2 pi by 4, and the second shift is 2 into 2 pi by 4, which we have seen just now, and the third shift will be 3 into 2 pi by 4. So we'll see that also. Let's see here. So here we have shifted 3 into 2 pi by 4, that's 3 pi by 2. So it means we are shifting it by 6 into pi by 4. So if you shift this by, so and you will be getting this spectrum. Basically, you can see this is shifted. You will be getting this one, and for this you will be getting this one. Okay, and so on. So, but however, this one will not come within the range. This one will not come within the range of minus pi to pi, as well as this will not come within the range of minus pi to pi. Need not to worry about that. So we are just looking at from minus pi to pi. So finally, basically, uh, you got the three shifts. The first one is the red one is the original one. The black one is the first shift. The light blue is the second shift, and this one is the last shift. Now I will add all these spectrums. Okay, so basically I have just shifted it over here, over here. So add it over here, and these also shifted over here. These also shifted over here. Okay, and these are shifted here. And these are shifted here. So you can see here basically now we have seen the complete picture whatever will come from minus pi to pi. So one thing which you can clearly observe that this is the spectrum which you are getting. However, the next step which is important is the scaling of the axis. Okay, so I will just plot it on omega y, and omega y is nothing, it is equal to 4 into omega x. So the new spectrum, say from let's plot from minus pi to pi only. So you will be getting something like this. Okay, so that's the spectrum you'll be getting from minus pi to pi. One thing which I have not marked over here is the scaling factor. The amplitude for this will be 1 by 4 compared to the original spectrum of V omega. Okay, if that the peak for the V omega was at, or the magnitude of V omega was at 1, now this is Y omega. Now the magnitude of the Y omega, the max of basically the max is equal to 1 by 4. So that's one thing. Now let's take another example for the case uh, when the d is equal to 4 and k is also equal to 4. When d is 4 and k is equal to 4. Basically, when the k is equal to 4, call it uh, we call it even band position. Even band position. So in that case, let me just sketch the spectrum of V omega. So the V omega, that's the output of a filter. Say it is something like this. This is 3 pi by 4. This is your 4 pi by 4. And here minus 3 pi by 4 minus 4 pi by 4. Okay. So if you apply the same thing, same procedure, the shifting and all those things, you need to produce, it will produce, this spectrum will be added with three more shifted spectrums. Okay, first shift will be 2 into 2 pi by 4. The second shift will be 2, 3 into 2 pi by 4. The third one, uh, sorry, the first one will be 1 into 2 pi by 4. Okay, so first shift, second shift, and the third shift. Then all these replicas you will be adding, and obviously you need to do scaling of the amplitude as well as after that you need to do the scaling of the you need to do scaling of the x-axis or omega axis basically. I mean, make it omega y is equal to 4 of omega x. Anyway, so I'm just finally sketching the output of all these things. So what you will be getting at the end, something like this. This is pi, and this is minus pi. Okay, and this is your y omega basically. So this shape you will be getting, and you can also observe that there's an inversion of the spectrum of the signal. Okay, so that's happening only uh, when you have k is equal to 4. Okay, and that can be easily avoided by just doing one more processing after the down sampling. That is, the output of the downsampling was this, so you can further do a processing to this system. Y prime m will be equal to minus 1 to the power m by m. I'm not going to explain that part, but you can easily invert, undo the inversion uh, by the simple process, which is going like this. Okay. So that's the thing about the downsampling. So the same process of the band pass interpolation by an integer factor I uh, can be performed, which is nothing. That process is the inversion of that, the band pass decimation. Uh, the process of band pass interpolation by an integer factor I is the inversion, the inverse of that of band pass decimation. Okay. We have seen a band pass decimation, but the band pass interpolation is the thing that's the inverse process of this of that of the band pass decimation, which I'm not going to explain. You can just read it yourself. Thanking you very much.